Hello, Serious Survivor here, and today we're going to talk about how the drive system supplies power to the robot's motors on an ABB IRC5 controller. And it's a pretty simple concept, even though it may seem complex at first. We're using transformer principles, basically, to use a device called a resolver to very accurately determine the position of a robot. Resolvers have taken the place of encoders quite rapidly over the last few years in most robotic systems that you'll run across. And the reason is a resolver does not need calibration, a resolver is much more accurate than an encoder, and a resolver is much easier to work with. We don't replace resolvers, we replace motors. Every motor on the IRC5 robotic system has one resolver per motor and generally one motor per axis. So what is a resolver? Well, a resolver is an analog device. But first, to understand a resolver, we have to understand a transformer. We have a transformer. We basically have two windings. We excite one side, our primary, with an electrical charge. That will create an electromagnetic field, which in turn induces a charge onto the secondary side. The basics of any transformer circuit. And that's the whole idea behind the way that a resolver works. The difference is, instead of a standard transformer like this, the resolver adds a third winding, or a third pole, as it's called. So let's look at how this works here. The resolver is a device that looks like a ball bearing. If you take the cover off the motor of a robot on an ABB IRC5, then you'll see the motor shaft protruding out the back side. And at the end of the motor shaft fixed to it, it looks like there's a ball bearing on it. And that ball bearing will have a small little connector come out of it. So if I take the motor cover off, I'll see the back of the motor shaft, and then I'll see what looks like a ball bearing. That ball bearing will have a set of wires that come out of it. This ball bearing is not a bearing, it's a resolver. Now inside the resolver we have this type of setup. We have one winding attached to the motor shaft. We have a cosine and a sine winding fixed to the motor case, situated exactly 90 degrees relative to one another. So what happens with this process is we excite this winding, the rotor winding. There's a couple of wires running to it, and we excite this winding with a 14 volt peak-to-peak charge. And it's at 10 kilohertz is the frequency. So we excite this winding, and through just the general principles of physics, when we excite this winding, it will create an electromagnetic field, which in turn induces a charge onto these two secondary windings. So we're basically inducing an electrical charge onto the two secondary windings, the sine and the cosine. Now these windings also have a set of wires. And those wires run down to the base of the robot. If we look at the robot, we've got the base, we've got the arm, and we've got the wrist. Now on the back of the robot, you have a base plate. For most of them, it's going to be right about here. You have a base plate that can be taken off. If I stand behind this robot and I face the rear of the robot and take that base plate off, in the bottom right-hand corner, right there, is a device called the SMB. SMB stands for Serial Measurement Board. So that's Serial Measurement Board. Now what this board does is it analyzes the charge that's induced onto these two windings and converts them into what's called a DIN, or digital incremental number. And this digital incremental number for a 3-pole, 1, 2, 3, or 3-winding, 3 poles, resolver, this digital number will be between the values of 0 and 12,287. That gives us a grand total of 12,288 known positions. So 12,288 positions that the SMB recognizes in one rotation of the motor shaft. Now that's extremely high accuracy. That means we can position this robot as accurate as to 1 out of those 12,288 positions. This is extremely high accuracy. Now there are more accurate robots on the market and resolvers on the market, 4-pole, 5-pole resolvers, in which you've got over 20,000 positions, known positions in 360 degrees. But today we're talking about the 3-pole. So that's the basics of how a resolver works. So what happens is we excite the rotor winding. That induces a charge onto the 2 secondary windings. Then that charge, that electrical charge, flows across the wires, just flows across the wires down to the SMB. Now the SMB sees that charge as 3 sine waves. It sees it as 3 sine waves. 1 sine wave for the rotor winding, and this one's never going to fluctuate. 1 sine wave for the cosine winding. And depending on the angle of the rotor winding to the cosine winding will give us fluctuations or variations in that waveform. Then you have the third waveform, which is our sine winding. And depending on the position or how far my motor shaft is rotated relative to this sine winding, it will produce fluctuations or variations in this waveform. So these 3 waveforms are simply transmitted across these wires to the SMB. The SMB looks at these waveforms. The SMB has 12,288 variations of these combinations of waveforms. And each one of those variations represents 1 increment or 1 position of rotation of the motor shaft. So the SMB can detect 12,288 different positions of that motor shaft. And they go from 0 to 12,287. So that's extremely high accuracy. So now let's look at the process overall. Now that we have a general idea of the way a resolver works, now check out the channel. I've got a resolver video coming out very soon that goes extremely in depth on this process. But for now, we're going to look at it with the generalized form, and we're going to incorporate this into the drive system, how the robot knows where to go, how to get there, and how fast to get there. So, there are several devices that comprise what's called the drive module or the drive system on the robotic controller. The devices that make this system up are the motors. Inside the motors, we have the resolvers. The resolvers communicate directly to the SMB. And I use that word communication very loosely because it's not a two-way communication. We don't send a signal to the resolvers. We simply supply a 14-volt peak-to-peak charge to the motor shaft winding, the one that's attached to the motor shaft. And from there, it will induce a charge onto the 2 secondary windings. There is no signal sent to them, and it's not really a signal we're receiving back from them. The resolvers do not tell the SMB what position they're in. The resolvers simply supply an electrical charge that's induced upon them, supply that electrical charge back to the SMB. The SMB then functions as an oscilloscope, and it looks at the sine wave of that electrical charge it's seeing. And then the combinations of the 3 sine waves is able to accurately determine how far that motor shaft is turned. So it's a complicated process, but it's simple on the operator or programmer side because we don't interact with this too much except when we're talking about it like this. So the SMB, that's a component in the drive system. The SMB, a cable running from the base of the robot goes to the bottom of the cabinet, into the cabinet, and connects directly to what's called the axis computer. You may hear some people refer to the axis computer as the axis controller. Same device, no matter what they call it, same device. The axis controller is communicating directly with the MC, or the main computer. So this is the main computer. Now, the axis computer is also connected directly to our 6-pack or 3-pack. Our 6-pack or 3-pack is our main servo drive unit. For robots larger than the 2400 series, they will use a 6-pack. Now, the thing that we need to remember about the 6-pack is the 6-pack operates on 700 volts DC is what it supplies to the robot motors. A 3-pack, this is the type of pack or servo pack that we use on a 2400 series and smaller. This is a 2400 series or larger than the 2400s. And with the 3-pack, it's only supplying 370 volts DC. So 2 different voltages there depending on the size of the robot. With a 6-pack, it's a 1-unit device. It's also called the main servos, is what some people will call it. These are all the same thing. The axis computer there, main computer, SMB, and the motors and the resolvers are one. So the main servo pack, main servo drives, main servo unit, whichever name you like, because if you look at the prints, it uses all 3 names in the prints. So if you have a 6-pack, then each one of those individual packs control 1 axis, and they're supplying 700 volts DC. If you have a 3-pack, then that's 3 packs built into the unit, and each pack will control 2 axes, and they're supplying 370 DC. Now, the main servos are connected to a device called the rectifier. A couple of things to remember about the rectifier. The rectifier takes a high AC voltage incoming and transforms and rectifies that to either 700 DC and 370 DC, and then it supplies it to the main servos across a bus bar. And that bus bar, the names for the bus bar, the controller will refer to it as the DC link voltage. If you see anything that refers, an error that refers to DC link or DC link voltage, it's talking about right here. This is where your problem's at. The rectifier has an incoming 480 to produce the 700 DC. But for the 370 DC, it has an incoming 262 that produces 370 DC. And both of these are AC voltages incoming. Okay, so they're coming directly off of the transformer in the rear. For large robots, 480 directly to the rectifier, and it's transforming or rectifying that 480 into 700 DC and supplying that to the main servos. For a small robot, we have 262 AC coming in, and it's transforming and rectifying that 262 to 370 DC and supplying it to the 3-pack for small robots. So that's the distinction between the power supply for large robots and small robots and the cutoff point. A large robot is larger than the 2400 series. A small robot is 2400 and less. So let's look at how this takes place. Well, if it starts in one location, it has to start with the resolver. So if we have the motor, and we have our resolver in the motor, and power onto the system, basically what's happening is we know the resolver internally, you got a winding on the motor shaft, then you have 2 windings fixed to the case of the motor at 90 degrees to one another. So we're exciting this winding. It's inducing, or it's creating an electromagnetic field here, which induces a charge onto the 2 secondary windings. So for those 3 windings, we basically have 6 wires coming from out of the resolver, and all these wires go down to one place, and that's the SMB. The SMB sees this induced or electrical charge in the form of sine waves. You can almost think of the SMB as part oscilloscope. It's looking at this electrical charge that's induced here in the form of a sine wave. So it's going to see 3 sine waves. And you know, these are going to vary depending on the position of the motor shaft. So the SMB sees these 3 sine waves. Now what it does when it sees these 3 sine waves is it compares them. It runs a series of formulas and then it compares them to what it has stored in its memory. And it says, hey, these 3 sine waves match up to position number, we'll use 5,000. We know that the 3-pole resolver has 12,288 increments, or it has 12,288 distinct positions that it can put that motor shaft in 360 degrees rotation. So these waveforms coming from the resolver simply represent how far that motor shaft is turned. So how far it's turned will match up with one of these numbers. So the SMB looks at the set of waveforms, and the waveforms represent how far that's turned. But the rest of the system's digital, so it can't understand these waveforms, so they have to be converted into a digital incremental number. Now once they're converted into the digital incremental number between the value of 0 and 12,287, then that digital incremental number is sent to the axis computer. So the axis computer receives that digital incremental number for each axis. Now it knows the position of the motor shaft for each axis on the robot. And the axis computer also knows the gear ratios, so it knows, if it knows the position of the motor shaft, then it can apply the gear ratios, and at that point the axis computer has determined the exact position of each axis on the robot, therefore determining the exact position of the entire robot. So now, by receiving this digital incremental number for each axis, the axis computer now knows the exact position of the robot. At that moment, it receives from the main computer what's called a profile. So from the main computer, a profile is sent to the axis computer. And this is transmitted across a RS-485 serial cable, directly from the main computer to the axis computer. So the main computer, this profile is simply telling it where to go, where the robot needs to go. The profile is where the robot needs to move to. I could be jogging it with a joystick, or maybe I'm executing a program. But no matter what I'm doing, the profile represents the next place the robot needs to move to. And you know, it's going to be very minute. So the axis computer has the real-time values of where the robot's at. It now knows where the robot needs to go. So it then calculates two pieces of information. And this is called our speed and position control set points. So the axis computer now determines the speed and position control set points for each axis, or basically how far to rotate and how fast to move each axis to get the robot to where the profile says it needs to go. Those are our speed and position control values. So this is how far and how fast each axis needs to move to get to the next position. So this information is then sent to the 6 or 3-pack, depending on which kind of robot you got, 6 or 3-pack, or our MS main servos. So it sends the speed and position control set points to the main servos. The main servos at that point in time see the position and speed control set points and said, well, okay, the axis computer needs us to move each axis this far, position control, and this fast, speed control. The main servos then determine the amount of current that will be necessary to do that, and that's called the current control set point. So the main servos determine the current control set point. So now the robot knows how far to move each axis, how fast to move each axis, how much current will be necessary to get the robot to the next position. So the main servo then orders the current from the rectifier. From the rectifier. The rectifier then immediately supplies the current to the main servos. The main servos then supply the current to the robot motors. The motor moves and the process continues. And this is a continuous cycle, a continuous flow of information. When the SMB calculates this set of waveforms equals this digital incremental number, then it doesn't wait until the process is complete to begin a new calculation. As soon as one calculation is made, it's analyzing the data again. This is a real-time flow of operations that occurs in less than 5 milliseconds. So this process is extremely fast, and if it's interrupted at any point, it will fault the robot out with a system failure. DC link voltage, drive unit communications, main servo communication. These are some errors you may see with this side of the circuit. Resolvers unable to determine your correct X and Y values for your sine and cosine. You'll see that on occasion as an error. But just going over it again, the way the system works is it starts and ends with the motor. The motor inside the motor has a resolver. As the motor shaft turns, that resolver, the motor shaft winding turns. we know we're exciting that winding with a 14 volt peak-to-peak charge, which in turn induces an electrical charge onto the two secondaries. So those waveforms are transmitted or sent basically in the form of an electrical charge to the SMB. The SMB looks at those waveforms, compares them to what it has in memory, and then runs a series of mathematical calculations to convert them into a digital number between the values of 0 and 12,287, which gives us 12,288 total known positions in just 360 degrees rotation of the motor shaft. So it sends that digital incremental number to the axis computer. The axis computer looks at that number for each axis, and it now knows the exact position for that axis. So it then receives a profile from the main computer. The profile is telling the axis computer where the robot needs to go. So from there, the robot calculates where it's at to where it needs to go and determines how fast to move each axis and how far to move each axis to get it to the point the profile says it needs to get to. Once it determines the speed and position control set points, it sends that information to the main servo drives, main servo units, your 3-pack, 6-pack, whichever terms you prefer. Sends the information there. And from there, the main servos determine how much current is necessary to move the robot this fast, this far. And that's called the current control set point. That current control set point is then sent to the rectifier. The rectifier is not a very logical device, so it doesn't make any decisions. It simply supplies the current that it's ordered to supply. The current is then sent to the motors from there. The robot moves, the process continues. Now, this is just an introduction to the drive system, and we're going to be talking in future videos in depth about the electrical and electronic system of the ABB, of the KUKA KRC2, and the KUKA KRC4. Trying to get a lot of these videos put together to make a very informative series. So just be patient, please, because I'm going to get them out as quick as I can. So I will be bringing some very valid and some very informative videos out to try and help as many people as I can when they're operating these robots, troubleshooting them, programming them, and so forth. And I hope you enjoyed the video. I hope you found it informative, and I hope it helps out. Thanks for watching, and for now, Serious Survivor, out.